Hi, everybody, and welcome to another Altinity webinar. I'm your host, Doug Tidwell, and we're very happy to be joined today by Alexander Zaitsev, Altinity co-founder and CTO, and a ClickHouse expert since 2016. Today's topic is Apache Parquet, which, as you probably know, is an open source column-oriented data file format that's optimized for speed and efficiency. A couple of housekeeping notes before we start. This webinar is being recorded, so you can watch it again later. Have some friends over, enjoy the festivities again. Also, I'll be monitoring the chat for your questions and comments as we go. At the end of the presentation, we'll answer your questions as we have time. So Alexander is going to show the state of Parquet support in ClickHouse today, look at performance improvements over the last year, and talk about ways ClickHouse's Parquet support can be even better. So with that, let's get started. Alexander, the floor is yours.
Thank you, Doug. So let's get started. First of all, who are, just in case we have some new people joined. We are Altinity. We're ClickHouse evangelists for 8 years almost. We collected a lot of expertise and contribute to ClickHouse with ClickHouse itself, with some ecosystem projects. We're authors of Altinity Kubernetes operator for ClickHouse, and we operate ClickHouse and Kubernetes a lot. But today we will talking about something different, about how ClickHouse works with Parquet. We'll discuss Parquet file format, do some performance benchmarks, and at the end we'll talk a little bit about the future of Parquet and ClickHouse, what we can expect and what we can dream of. So first of all, let's remind you a little bit about ClickHouse itself. So ClickHouse is a database. It is a very great database that we all like. It is SQL. It runs everywhere from Android phones to the clouds and big clusters. Thanks to very universal architecture that ClickHouse is built in, and actually it's a very simple architecture. We've shared nothing. It stores data in columns, and we'll talk about that today quite a bit. Internally, it employs a lot of optimizations around vectorized execution of queries, around parallelism on all levels. And as such, it scales to very big systems. So the biggest known installations of ClickHouse in the world, they operate tens or hundreds of petabytes of data. And thanks to original creators of ClickHouse and the current maintainers, it's open source with very permissive Apache 2.0 license, so we can all use it for our applications. ClickHouse main storage format is merge tree, and it is important to cover it first before going to Parquet, because it kind of resembles Parquet in several properties, and vice versa. So what is ClickHouse merge tree? It is the special storage engine that defines how data is physically stored in the disk. And probably the two main properties about the storage is partitioning and ordering. Partitioning in ClickHouse, it means the separate sections of the data that never intersect with each other. Quite often, partitioning is performed by date, but it's not a requirement. By date, by month, by something date-based, but could be others as well. The ordering is another very important characteristic of merge tree. It defines how the data physically sorted inside the partition, or inside parts, which are pieces of partition. Those two important characteristics, they drive ClickHouse famous performance, because using partitioning and physical ordering of the data, it's possible to build very efficient and high performance systems. Merge tree is writable. You can write to it many times. Usually it's recommended to write in bigger chunks, but you can write in single rows. And the special background process in ClickHouse, it takes those chunks that were inserted separately and creates a bigger chunks inside merge tree in order to facilitate efficient query processing. Originally, merge tree has been designed as a format for physical storage, and therefore ClickHouse has a lot of optimizations for block devices, starting from OS page cache, OS level Linux page cache, where ClickHouse kind of expects that the data may live in the cache and tries to use it efficiently. For example, it tries not to invalidate cache with some heavy writes, but instead, if there is a heavy write, it can go directly to the storage bypassing the cache. Or if there is a heavy read, there is no need to put it in a cache because it may invalidate a lot of smaller pieces of the data, but it can be streamed directly to the client. So kind of like that. It is just as a background. There are four main properties of a merge tree. It is columnar, so every column is stored as a separate file on a file system. It's possible to combine columns together, but internally it's still a separate structure which is stored sequentially in RAM. Column is stored sequentially in RAM and in storage, not at all. ClickHouse uses a lot of column encodings in order to store data in columns more efficiently compared to some other databases. And on top of that, it also employs compression. The physical order of the data and sparse index, which is part of this merge tree implementation, helps with efficient queries. I don't want to go into a lot of details about merge tree, but just let's remember or memorize those three or four main properties. Now let's look into Parquet. Parquet is not a database at all. It is a file format. Originally, it has been designed for Hadoop ecosystem, for Spark and applications like that. And as such, it is very widely used in data lakes. And it could be consumed by many different systems, many different databases, streaming engines like Kafka, and so on and so forth. It is extensible, so it's not a closed format. It is open source. It's also a part of Apache Foundation, and it may be extended by different data types, by different or new data structures, and so on. So it's not fixed. It is being developed over time, and it is being improved as we speak. Parquet format has very similar characteristics to merge tree. If you look into that carefully, it's also columnar, and merge tree is columnar. It also have column encodings similar to merge tree, which also has column encodings. It also uses compression. Merge tree uses compression. It also uses column metadata to help with query execution, and this is similar to what merge tree does with its sparse index and stuff. So they are those two different things. One is a database engine, and another one is a file format, is quite similar. And we will discuss those similarities in a few minutes. So since Parquet format is kind of similar to merge tree, we may expect that ClickHouse can work very efficiently with Parquet, and we'll figure out if it's true or not. Let's start with very simple stuff: how to read data from Parquet files. How to read and write data to Parquet files. First, we'll start with writing, because we need to prepare data for the tests. I took the data set that we use quite regularly for different benchmarks. It is called On Time. It contains airline flights in the United States for many years. It is not very big. It is about 200 million rows. But from one side, it is big enough to run different queries and see the difference. And from another side, it is small enough to make testing fast, to load fast, and so on and so forth. So if we take this on time, which is stored in ClickHouse and emerged table, we can write it into a Parquet file on a local file system using a very simple SQL command, insert into function file. ClickHouse has a feature which is called table function that are widely used for integration with external systems. And ClickHouse can usually read to table function from table function and write to table functions. Examples of table function we will see today. This is file, for example. We will see S3 table function, URL table function, and probably some others. But there are much more. So once we execute this query, which will take quite a bit of time, and we will see why later during the webinar, we can see the file on a local file system in a var-lib ClickHouse user files folder, which is something like 5 gigabytes of size, created yesterday. And the location of this file is actually configurable. So ClickHouse by default stores files in special folder user files, but you can move it to somewhere else if you need to. So this is a single file. Sometimes it is convenient. Sometimes, especially if you have big data set, it's not very convenient. So ClickHouse has a different way to write bigger tables into files, and it is called partitioning. So how it's performed? In order to write partitioned Parquet file, you need to do two things. You need to add partition by expression into your insert statement, and you need to add partition ID macro inside the file name. What will happen for every year in the original table, ClickHouse will create a special file using the year instead of the macro ID, macro partition ID. Once we execute this query, we can check the file system once again and see that for every year, we have a separate Parquet file, which is quite convenient. So we can manage them separately, move them separately, but not only this, it's also quite important for performance. There are other ways to write Parquet files. ClickHouse in recent versions introduces the syntax select into out file, which resembles MySQL and some other databases, with a lot of different options that you can apply to this. The only warning is that this statement, so if this insert is executed on the server, because the file, it is sent to the server and executed on the server side and is written to the server directory, then this query will be executed on a client and written to the client file system. So if you run this, it will write to your current working directory from which you started ClickHouse client, or if you're using web client, I even don't know where it's going to write the result. So be careful with that, and I personally don't recommend to use this syntax, but instead use insert into file table function. Once we have the data in Parquet, let's start to query it a little bit. We will start with very simple queries, and then we'll go to more and more complicated ones. The simplest query is to write a count, and we can see the count is 200 million rows, which is expected, and it is pretty fast. 50 milliseconds is a good time. We can also query files using a globe syntax, which allows us to query across multiple Parquet files, and it is very, very important feature for working with the large data sets. We can similarly calculate the count for ontime_star Parquet, which will select all files for all years that we just created. We will get the same result. I just removed it for the sake of space, but it is faster, and we will see it later on that when we query multiple files with a glob, it is usually faster than querying a single file, and there is explanation for that. We can go to a more complicated queries. So like here we are running some grouping, and if you want to figure out the distribution across days of the week for several years. And again, if we go to a single file on the left, we get result in 600 milliseconds. And if we go to our partitioned multiple files, we'll get the same result, but 5 times faster, which is remarkable. The performance testing will be done in more detail a little bit later. For now, just let's remember this interesting fact. Similarly to writing a reading to file, we can write and read to S3. There is a function of S3, and we can write to S3 with partitioning as before, and we can query S3 bucket similarly as we will query in the local file. The only difference is that sometimes in order to access S3, we need some credentials. For public buckets, there is a special keyword in ClickHouse, no sign, in the recent versions that instructs that no credentials and no signature needs to be provided. If you are using buckets without public access, then ClickHouse has a bunch of different ways how to configure S3 security. This is not a topic for this talk, just to give you a very, very quick overview. So ClickHouse can take credentials directly, provided directly to the call of S3 function. You can use named collections where you can specify those credentials and then reference them from when you query the bucket. You can configure EM role on a ClickHouse VM side and use this role-based access to S3 bucket. Or you can use some environment variables to provide S3 connection characteristics. A lot of different options how to securely access S3 buckets. Just for the reference, we're not going to spend a lot of time here. Next, let me do the following. I will explore some public Parquet files in the web. So what I literally did, I just Googled for a public Parquet dataset and picked 2 just to demonstrate how you can query some public Parquet data from ClickHouse very easily, or not very easily sometimes. So this is the first example. I just found the dataset from Kaggle tests, from Kaggle benchmarks, or training data, if I recall correctly. This is different data, but also related to flights. And you can very easily query it from ClickHouse, right? I can query the first row from a GitHub and can see the result. Very easy. The max HTTP GET redirects, I had to set it because apparently GitHub makes some redirect to the data itself. And by default, ClickHouse doesn't allow HTTP redirects. You need to allow it explicitly with a setting. Next data set is more interesting, and we'll spend some time digging into it. These are some data set for genetics. If I read it correctly, it's not important right now what exactly the data is, but it is public, it is open, and we can access it and download it. But not very easy, because the standard ways that are provided by this platform for downloads are quite limited. You can use FTP, you can use a Google bucket, but somewhat strange, or you can use what else? rsync, right? It's not something that ClickHouse natively supports. But let's try to look into the data, and maybe we'll find a way how to read it. First, instead of FTP, we can use HTTP. So apparently there is HTTP server running. So we can go to this folder and see that there are a bunch of Parquet files stored here. And probably we can try to read one of them, and they are available. And yes, voila. If we run describe on URL that references this Parquet file that we could just see, we can see the table structure. So ClickHouse can use describe command in order to describe the structure of remote Parquet file. So we can see that this is quite complicated structure with a lot of arrays, so with a lot of tuples, but this is real data. So we can try to load it. And of course, we can write a query. So just query it directly and see that this is something that we don't know what it is about, but if we need it, we can use it very easily. Here, we are using URL function, which is kind of similar to S3, but it doesn't have a lot of S3 optimizations. It is more like a curl command. What else we can do with this data? Actually, there are a lot of files, and we may want to load it into ClickHouse or make some tool to read all them at once, because there are 200 files, and if we want to look into the data in a wall, it would be complicated with 200 files. So what we can do, for example, we can create a table in ClickHouse and load all the data from those Parquet files into ClickHouse. So for that, we can do this first. This is a create table statement. And we use a structure of Parquet files in order to create this table. You see this no data part in a create table. This is also quite a new ClickHouse feature that allows you create table without populating any data. Because usually, if you create table as select, you expect that some data will be there. But with no data, you can create table without any data. Okay, next, what we can do next? Next, we can actually read HTML. So we can read the page where those links to the files are stored and see. First, we can read HTML from ClickHouse using the same URL function and the special format TSV raw. TSV raw is translated as tab-separated raw format, but it doesn't do any extra pre-processing of the data. It returns it as is, and this is important for us. And it breaks by line ends, which is also convenient and pretty typical for HTMLs. So here we have a result with every line from HTML page as a separate. So this is quite good. We can see that there are names of the files here, and we can try to extract them with what? Of course, regular expressions. So this is a query to extract file names. We read the same page, right? But as a string here, we add a structure and then use extract function, which is a regular expression parser in ClickHouse, in order to parse those file names. So what's next? Next is a little bit hardcore-ish, I would say. We have several ways to handle this data. One of the possibilities is to generate a lot of insert statements. For every file on this page, we can generate a separate insert statement and just run it. So we will run 200 statements, and it will populate the table in ClickHouse with the data from those Parquet files. So this is an example how we could do it. The first, the upper part is a query that generates insert statements. So it's usual ClickHouse query. It constructs those insert statements from the file names that we extracted earlier from HTML page. So this is one approach. Another approach, we can create a giant, huge table that would union all individual these URL references. So this is again example how we can create such a huge create table statement, but this is not very convenient, right? It is huge, it is hard to run, it is hard to change, and actually it's not very efficient to execute as well. Is there a better way? Apparently it is. I was thinking what we can do and decided to create a special database. And in this database, for every file, we can create a separate table with engine URL. This engine didn't appear yet, but it is the same as URL table function, but it allows us to create a table which is statically mapped to the particular URL. So these create table statements that we generated, they create a table inside target all database. The name of the table exactly matches the name of the file. The engine matches the URL of particular Parquet file on the web. And if we query this table, we will see Parquet data. It's kind of mapping of ClickHouse table to remote Parquet data, which is convenient. And if we run those create table statements, we can then show tables from target all and see that we have a lot of tables which are named exactly as Parquet files. So we can query them directly. But our goal was to query all Parquet files together from this data set. In order to do it, we can use the merge table function, which allows us to combine multiple tables that matches regular expressions together. So we have regular expression which matches all tables that end with Parquet. And when we do it, we can run a query, see that actually those Parquet files were pretty small one. For all 200 files, it's just 60,000 rows. And we can also check rows for individual file as a sanity check using a special virtual column file, just a demonstration of yet another ClickHouse feature. So at the end, what we just did, we took the external data set, which was placed on the web, and wrote a simple parser on ClickHouse to parse HTML page. And using this parser, we created a special database which was mapped to this data set, to those 200 files on the web. And now we can query it from ClickHouse, do any sort of analysis, any sort of queries, and so on. But that was pretty inconvenient and required a lot of work. So actually, ClickHouse has a simpler way to do it. It is called overlay databases, but unfortunately, it's not supported for URL, but it's supported for file system, it's supported for S3, and it's supported for HDFS. I can show it from for file system. We create database using a file system database engine. So we were talking about table engines, but ClickHouse also allows you to specify database engine. And this is an example of where a database is mapped to a folder, and all files in this folder, ClickHouse can think of them as tables. And since the extension is Parquet, ClickHouse understands that this is a Parquet file, and we can run any queries from this table, which is mapped to a file. Maybe for file system, it's not so cute, but if we have S3 bucket with a lot of files, we could map database to S3 bucket. We could create database to a bucket where we store our on-time files, and we would see it as tables in this database. So this is quite a cute feature, but at the end, it does almost the same as we did with parsing this HTML page, etc., but without any parsing. ClickHouse could do it automatically. Now let's talk about performance. It's a very interesting topic, how fast ClickHouse can read and write Parquet. So for performance tests, I also took on-time data set and selected for queries. And as a contenders, I run 4 different things. The queries over original merge tree table, the query over on-time Parquet file, which is a single file that contains all the data for on-time, the query over our partitioned version of on-time, and the same query about the data which is stored as S3. So we will have 4 different tests, and we will run 4 queries. First query is very simple grouping. So no filters, several columns, and grouping. Second query is a bit more complex. We will have a filter on year, which is a partitioning column, so it should be very efficient, and also simple grouping and aggregation. The query number 3 adds a filter on non-partition column. So this is yet another column, and it will require more work from the database, potentially a full scan now. And query 4, it adds a filter on a column that is a part of merge tree primary key. So for ClickHouse, it is important. For Parquet, Parquet doesn't know about primary key, and also doesn't know about ordering, that we will see in a bit. So for Parquet queries, I had to add to date conversion because apparently Parquet doesn't have date data type. So the flight date was stored as an integer. So the special type conversion is required. Here are results. And those are quite interesting. First of all, merge tree, which is a blue bar, is definitely the best. The smaller is better here. It executes constantly below 100 milliseconds, reaching its minimum on a 4th query, which uses primary key. Their query time is 20 milliseconds. Very, very fast. The Parquet showed very different results if I was using the single file or partitioning files from multiple files. The single file was under a second, but it's pretty slow compared to ClickHouse. But with multiple files, Parquet performance was only 2 to 5 times slower. And in absolute numbers, it was outstanding. 200 milliseconds for a query. This is very good. You probably don't see here results for S3 because in this test, the query and Parquet file from S3 was really slow. It took something from 2 to 7 seconds per query. And these results are unexpected. I suspect there is some regression in ClickHouse because when I was running the same benchmarks last year in May, Parquet performance was better. Now I'm using the latest ClickHouse version and it is degraded. Our engineers, they are trying to figure out why it's happened. I suspect there is something changed in ClickHouse default settings about parallelism, how aggressively it uses network when fetching data from S3. So we are still investigating that. But for now, in this benchmark, performance from S3 was not very good, quite opposite. I also tried the following. I tried to sort data in Parquet the same way as it's sorted in merge tree. In merge tree table, the data is sorted by care and flight date. And if I do the same in Parquet, maybe Parquet will be smart enough to use this ordering when I filter by flight date. But it didn't happen, unfortunately. So yes, the data size was a bit smaller thanks to this ordering, but the performance of queries, I didn't see any difference. So unfortunately, Parquet doesn't understand, or probably ClickHouse cannot communicate the extra knowledge about the data that data is sorted. Maybe in the future, it will be supported. The next topic is compression. It's both merge tree and Apache Parquet they are known for good compression. But what are the real numbers? Apparently, the on-time database, it's not a good example. So on-time table, it's not a good example. The compression ratio in ClickHouse is just 3.3 times. So this table is not optimized. So it's just uses all defaults, data types with no encodings, all defaults and all ClickHouse defaults. Compression is 3 times. But Parquet, by default, is much smarter. So as you can see, the size of a single file was 5.3 gigabytes. The size of a multiple files was even smaller because we partition data by year, and there is some locality of the data within a year. Because some airlines, they may have different schedules in different years. Some airlines appear, some airlines disappear. So the locality within a year definitely exists, and that helps with the better compression. So the compressed data is just 4.9 gigabytes for Parquet, and it is 14 gigabytes for ClickHouse. The first column in the left part of the slide is a 14 gigabytes. It is 3 times bigger. So compression in ClickHouse is 3 times worse than in Parquet. That is actually a very interesting result, and it's not in favor of ClickHouse. So definitely it's interesting to see why it's happening and if you can make it better in ClickHouse, and I tried it. First, let me introduce yet another ClickHouse feature related to Parquet, which is called Parquet metadata format. ClickHouse can read metadata which Parquet stores inside Parquet files that describes a lot of different things about Parquet file itself. So this is just a beginning of this metadata. Metadata is huge, so it's a huge JSON. But you can see that it describes a column. So first column is a year in this row block maybe. You see physical type, you see compression, you see encodings. It actually doesn't say which exactly encoding has been used. I think it says only about available encodings. And it says how much space it saved. So for this particular piece of data, the saving was pretty small, only 3%, because compressed size 120 bytes and compressed size 116. Actually, it's probably even worse. So the space saved is negative. But in total, Parquet is more efficient. And we can actually check efficiency by column if we extract extra data from Parquet metadata. Don't be frightened by this query. So this is something which has been constructed by one of very talented Altinity engineers. But it allows us to tie together columns with ClickHouse and Parquet file and compare compressed size. So this is a piece of those results. And I showed here the top columns that take the most of space in ClickHouse in this table. And for some of them, like elapsed time, delay, arrival delay, or arrival time, the difference is, so it's delta, not actually in percent, delta in times. The difference is 2 times. This is probably not too, it's significant, of course, but the difference for 2 columns that are highlighted in yellow, it's much bigger. It is 7 times difference. So ClickHouse size is 7 times more for this column compared to Parquet. So why is that? Let's take a look. And this is a very simple exercise that you can do on your data if you see something like that. First, step number 1, check the data itself and see what the data looks like. I can see that in this column, it looks like there's some range for the arrival time, something like that, which is a string, and string which is constructed very similarly. So I can expect that number of unique occurrences of the string is not very high. So I can convert it to low cardinality string, which is a dictionary encoding. And this is what Parquet usually does by default on all or majority of strings. So I can modify the column to low cardinality and check what the results looking into special system parse columns table. So now my column consumes 49 megabytes instead of 500 megabytes that we could see on the previous screen. So the difference is 11 times. So this very simple alter table, and for this particular column, ClickHouse started to take 11 times less disk space, and in this case, it is even better than in ClickHouse or in Parquet, because in Parquet it was 72 compressed, 72 megabytes. In ClickHouse we now have 49, so we are better. So what if we modify all string columns to low cardinality? Because if it helps with one column, maybe it will help with other columns. There are something like 100 string columns in this table. And we can do it with this trick. Also, this is one of my favorites. So you run a query for ClickHouse client that generates a set of alter table statements and feed them to ClickHouse client, which executes those statements one by one. And the beginning looks like that. So we start running those queries one by one. And at the end, we can check the compression or the data size. And we can see improvements, actually 30% improvement for compression, but it's still much worse than Parquet. Just to remember, Parquet was 5 gigabytes for this data. In ClickHouse, we still have 11. What we can do next? Let's try the last resort, change compression to ZSTD. It is ZSTD1. It is still not very computationally extensive. And we often recommend our clients to use ZSTD1 if there is some big column that consumes a lot of disk space. Now we will apply ZSTD1 to all integer columns. You can see type like int. For all integer columns, we'll run ZSTD and we'll see what will happen. That helped to improve compression 2 times. So it is 5.8 gigabytes, but we're still behind Parquet. So Parquet does something very special about determining the best compression, and it does it for the same row block. So when the data is inserted to Parquet, for every row block, for every column, Parquet tries to determine the best compression, and it is much more flexible and efficient that you can get from ClickHouse. Not much more, but it looks to be more efficient that we can get from ClickHouse. So this is actually a very interesting result. So Parquet is outstanding here. So that's it with compression. Let's look into a few other things, and then we'll have probably 5 minutes for questions. If you run Parquet workloads in ClickHouse cluster, then ClickHouse has very interesting features to distribute load for full cluster. For functions like file, URL, and S3, and probably HD files, there is a counterpart: file cluster, URL cluster, and S3 cluster. What it does, if you run the query using file cluster, it distributes the load across all ClickHouse nodes. The typical example, you can run a query or you can run insert statement. If you run select from S3 cluster, for example, you can insert the data to distributed table in ClickHouse, and it will be executed in parallel on all shards. If you query it, the query will be executed on all shards as well. This is kind of similar to distributed table, and it scales actually linearly. But unfortunately, unlike distributed table, it doesn't understand query semantics, and it doesn't rewrite queries when being executed. If you're new to ClickHouse or haven't looked very deeply into how distributed query works, ClickHouse does a lot of heavy lifting here. If you run group by, then ClickHouse does group by on shards first, and then sends a partial result to the initiator node. With those cluster functions, it's not happening. ClickHouse runs the fetch in a distributed fashion on all shards, and then results are being sent to the query initiator. So the more heavy lifting has to be done on query initiating, even though the workload is very distributed. And the last thing on performance, let's take a look at the write performance. We haven't discussed it yet. When we started talking about Parquet, I showed how to write data in a Parquet file. And in fact, that was the longest thing that I had to do when preparing this talk. It took more than 15 minutes, 16 minutes to write this Parquet file. This is very slow for ClickHouse. You can see the performance is 200,000 rows per second. What is this about? This is something very, very slow. Can it be done faster? Apparently, it can. There is a special setting, output format Parquet use custom encoder, that does totally the same job, but 40 times faster. 40 times probably because my machine that I use for those tests is 32 vCPUs. But it is even more than 32 times faster, 40 times faster. I was actually impressed. In 25 seconds, I could write the full Parquet file back to the file system. And you know what? It is even faster than inserting table to exactly the same table. So writing to Parquet using this custom encoder is even faster than writing to merge tree. Almost 50% faster. I was also impressed. For some reason, this output format Parquet use custom encoder setting is disabled by default. This setting is still considered as experimental. It has been added probably in version 23.7, but we can expect that it will be enabled by default in the future versions. Let's talk a little bit about the future, and we'll go to the questions. ClickHouse has published the roadmap for 2024, and there are two features that are related to Parquet in this roadmap. One feature is support for Iceberg data catalog. Iceberg is a distributed catalog for the data, and you can find about Parquet files in those locations from those catalog. So if ClickHouse would support it, it would be much easier to discover different Parquet data sets and query them and load them to ClickHouse and vice versa. The second feature which you can find in the roadmap is Hive-style partitioning. Frankly speaking, I have no idea what it is about, but it looks promising because Hive is also very popular processing engine for Parquet, and maybe there is something that can be shared between those two systems for better interoperability and performance. Multi-threaded writes, this is a setting that we had just discussed, the experimental feature, and it needs to be disabled by default for the high performance writes. So it needs to be enabled by default. We expect it to happen soon. And there were also some draft PRs for better support of complex data types, for better push down on certain things in the ClickHouse. They all help with better compatibility, with better performance, and we can expect more things like that from community. Actually, I'm not sure about Iceberg data catalog and Hive-style partitioning, but many features for ClickHouse, many features for Parquet functionality has been contributed by community. ClickHouse core team, they did a lot for performance, but compatibility work, this is a big credit to community. Another thing which is kind of interesting, we were discussing about Parquet in the same context as we were discussing merge tree. So we compared them side by side in terms of performance, in terms of compression, and one of the ideas that it's possible will be implemented in ClickHouse is to have Parquet as a format for merge tree. ClickHouse can merge tree on a file system is a set of files. So every column is stored in a separate file. There is a file for index, there is a file for metadata, but it's still a set of files. And merge tree has two different formats for parts already. One is called wide format, This is default columnar format. And there is also compact format when all the data is stored in a single file, which is very, very similar to Parquet. So what if we make a Parquet file format to be a part format for merge tree? In this case, ClickHouse could write to Parquet natively and read from Parquet natively. We could take Parquet files and attach them to merge tree table as a part. That would be a very cool feature. And if it happens, it will make ClickHouse data much more portable and interchangeable, intershareable with other systems. That's why we're very excited about possibilities of this feature. And by the way, if you are interested in this feature and want it to be implemented, contact us. So we're collecting interest for this. Let me finish. So Parquet and ClickHouse, we discussed a lot of good things today. It's very easy to work with Parquet files from ClickHouse when they're stored in a file system, when they're stored in object storage, HDFS. I didn't test it HDFS, but I know it works. We also found that Parquet compression is outstanding, and thanks to the way how Parquet automatically detects the optimal encoding and compression for every chunk of the data. ClickHouse is not as flexible here. It allows to define compression and encoding for every column, but it needs to be done by user, and this is for all column regardless of different parts of this column. We also could see that performance of Parquet from local files is also outstanding. It's very fast. It's comparable to merge tree, and it's faster than with many other databases. And we also discussed how we can explore remote Parquet dataset, even if they are accessible through some clunky HTML interface. We can still parse these pages and make the Parquet data to be queryable in ClickHouse. On the negative side, it's still hard to work with web server file collections, so when there's no good interface to that. And ClickHouse, or the way ClickHouse stores Parquet, doesn't fully utilize all Parquet features. For example, Parquet already has some indexes. It has some minimaxes which are stored in Parquet metadata. ClickHouse either don't store it because we took Parquet files for our benchmarks that were generated by ClickHouse. So maybe ClickHouse doesn't generate it, or ClickHouse doesn't use it yet. So these are improvements that, if they will happen, will improve performance of queries over Parquet data. It doesn't improve performance of writing and reading Parquet in full, but if you query Parquet data set with some where condition, that will improve performance and probably make it comparable to merge tree. Some best practices at the end. We usually recommend to use latest ClickHouse version for latest features, because ClickHouse evolves very rapidly. Some results that I could get 6 months ago, they're not true anymore. I always have to retest and recheck with the latest ClickHouse version. But if you go to production, then you need to be more conservative, and we highly recommend to use LTS or Altinity builds for production, which are being released with a 6 months cadence. We also, as you could see, if you store Parquet data in multiple files, you can get much better performance than using a single file. And the last is a cluster. Cluster functions is a great way to work with Parquet and ClickHouse clusters. And probably you have some bigger ClickHouse clusters that can benefit of that. That's it from me. There is some reference material that you can read. You will get those slides. And I'm open to questions. Thank you for your attention.
All right. Well, thanks, Alexander. That was fantastic. We do have a question from Yuri. I'll just read this. He says, does ClickHouse write Parquet files with special non-standard options? He says, we have a situation where a Parquet file written by ClickHouse was not accepted by Spark, probably a problem with the compression codec, but he's not sure.
ClickHouse doesn't use any special settings as far as I know. There are some knobs that you can tune in regards to this, but I would expect that this is a bug, not a feature that you could read it, that you couldn't read it from ClickHouse, from Spark. Last year, we have fixed a number of compatibility issues around nullable fields, about some nullable maps, tuples, whatever, and that could be a reason. It could be some incompatibility between how ClickHouse interprets this data and how Parquet interprets this data. Moreover, our K team, they did a lot of testing on Parquet compatibility, and they have found that the standard is very flaky. For some features, different Parquet libraries produce different results.
All right. Anyone else have a question or a comment? We'll keep it open here for another minute or so. All right. Well, it looks like that answers everyone's concerns. Thank you so much, everyone, for being here. We hope this has been useful to you. And we will see you again next month with another Altinity webinar. Cheers.
Thank you, Doug. Bye.